Numeral 6. This is Zircon. I promise we're only going to Roman numeral 8, which means we're almost done with all of these other gemstones. Those that are not incredibly popular, but they are beautiful and have significant value. Zircon is December's birthstone, so it has made it on the board with cultural relevance. And it's an incredibly affordable stone with a wide amount of geologic significance. So to a geologist, this is one of the most interesting gemstones that exists. Mineralogically, we should talk about it and its composition and its crystal structure. You can see it right here if you are ahead of me. So mineralogy and geology. Number 1, the chemical formula for zircon is ZrSiO4. So it's a fairly simple crystal in its composition, and you can see where the name comes from, right? From zirconium. Crystallographically, it's also fairly simple. It's not isometric, but you can see that there is a nice regularity to the crystal. It fits into the tetragonal system, and it tends to form kind of stubby, four-sided prisms that have a pyramid on the top and a pyramid on the bottom, so a bipyramid. In fact, so here's the column, the stubby four-sided columnar part. That's what we call a prism. And then here is the top of our bipyramid. We could even draw this if you wanted to. Why don't you try? So you'd have to draw something like that at the top, and then a stubby little bit here, and then you might be able to do it better than I can here. But there. That's what a typical euhedral zircon crystal should look like. So we need to label it, right? So we're going to say that it has the an A4. Remember that symbology to show the tetragonal prism. And then it's also going to have the bipyramid. What else should we say? Oh, Mohs, it's a 7.5 on Mohs, so it's a very hard mineral. It should survive in jewelry and in the alluvial environment, so it has good survival potential. It's fairly easy to chip, but we don't need to worry about that too much right now because it is good for jewelry. We're going to say here that it is one of the most important minerals in all of geology because it allows us to use a rock as a clock. Or another way to say that is we can age date a rock using zircon. So this is one of the most important gems, or minerals even, important minerals in geology. Technically in geology, we call this science that uses this, we call it radiometric dating. But you could also think about it as clock in a rock. Because what there is radioactive decay that goes on in the lattice of zircon. And if we can measure that using some sophisticated tool, then we can count how many half-lives have passed. So what ends up happening is that there is some uranium that substitutes for zirconium. And uranium is radioactive. And so what uranium does when it's in there, there's not a lot of it, like parts per million level. Well, it goes through radioactive decay to lead. And it does this at a set half-life. Right? That half-life just means that the parent decays to a daughter at a specific rate. And let's say if the half-life was 50 years, well then in 50 years, half of the uranium would have turned into lead. Well, the actual decay constant of this is something like 700 million years. But that's just how it works. Now, if you're interested in this concept, I do have another video on YouTube that goes into the science of geochronology. That's another way to say radiometric dating. And you can absolutely go watch that, even though I wrote it or recorded it for a different class. So anytime you hear about an age of the earth or an age of a rock, either in the news or in some science class, it's coming from this. Maybe we should say something like, this is how we, all ages on rocks. Or like, how old is the moon? Well, maybe we've done it using uranium-lead geochronology or a similar system. Or Earth. They're all coming from this kind of science. Well, let's move on from that. That's a whole nother lecture or two or three if we wanted to really dive in. The occurrence of zircon, thankfully to geologists because of all this, well, it's basically all types of rocks. Said rocks, get them. Igneous rocks, have them abundantly, and so do metamorphic rocks. So we can age date a whole, well, almost any type of rock you want using uranium lead. Now, gemologically, where do we actually mine the material? Well, we mine them from alluvial placers because most of the zircon that crystallizes in igneous and metamorphic systems actually looks like this. Now, this is a slightly, all right, and if you look at this, well, that's a beautiful four-sided prism with the bipyramid, just like we'd expect. But find the scale bar in this image. It's right here, 10 microns. So that's telling us that this crystal is like 100 microns, I don't know, maybe across and 200 long. What does that mean? Well, it's very much smaller than a millimeter. So even though they tend to occur in all these rocks, they're very small. And let's say this, let's say less than 1 millimeter in length and diameter. Terrible for jewelry, right? So when we actually find them, they need to be enriched and concentrated in alluvial deposits. And that's also made easier by the fact that it has a very high specific gravity. So I kind of didn't give myself enough space there. Let's say this. Let's say that they are found or mined from alluvial deposits where they're concentrated by river action. The reason for this, well, they have a specific gravity of 4.6, or I guess you could say density of 4.6 grams per centimeter cubed. So it's very dense. It's easy, therefore, to find them when you're like panning for gold, for example. Now let's move on to a little bit more of the gem side of this with a little bit of color and optics. We saw the color at the top of the page, and this was a dark red color, which would facet into a beautiful gemstone. And red is a very striking color that zircon can have, but can also have very, very many other colors. So we're just going to say that it occurs in many colors. The most common natural colors end up being reds, browns, pinks, oranges, right? That kind of warm side of the spectrum. But that's not what's bought. What ends up being bought in jewelry, and it represents 80% of jewelry sales, is blue. Jewelry sales is this kind of, it's a bright blue color. It's not a dark blue. Let me show you a very good example from the Omi Privé website. Here is, I'm going to make this one real big. I'm even going to, well, I can't fit it. Well, there you go. That's what we'll put in. This is a blue that is produced, why does it do that? Stop doing that. It's produced by heating. If you take a red, a pink, brown zircon and heat it to around 800 to 875, so let's just say like let's say around 850 degrees C, well, that brown color will go away and will produce this beautiful blue. And this has been very popular since the Victorian era, so it's been for hundreds of years now. And because of this, and 80% of sales, then what we need to say is that heating is very common. It is the norm. Heating is the norm for zircon. The last thing we should talk about is how zircon bends light, because it does. It has a very high birefringence, and what that produces is the double refraction, like in peridot and like in calcite. So let's say double, oh, that's not how you spell it. That's how you spell it in Spanish. Let's spell it in English though. Double refraction splits light into two rays. And when we have these two rays, we should see things doubled or repeated. And let's see if you can see it here. like if you look right in this area, and I don't know what kind of resolution your screen has, but the facets start to double, producing a blurring effect. So let's say that this produces a doubling of light in the stone, making things blurry. I think it's a really neat mineralogical effect, but it can reduce sometimes the value of the stone. And with that, I think that's all we need to say about zircon. See you next time as we move on to spinel, one of my favorites.